Greetings, welcome back. We are still in session 7. I would like to go through another example just to solidify our understanding of how a naive Bayesian technique works. Let me share my screen. This is part 3, Bayesian classifier. The slides are available for your offline view. Bayesian classifiers are statistical classifiers. As you have noticed, we have been using probabilities. They can predict the class membership probabilities, such as the probability that a given tuple belongs to a specific class. What does that mean? We want the event X, referring to the previous recording, we want the event X to be considered. And then the question is, if the event X has happened, would you play or not? So that's the class we are looking for. Class yes, class no. Bayesian classifier have shown high accuracy and speed when applied to large database. That's good news because obviously we don't want to do all of this by hand. There are codes available and all of that has been automated already. Bayesian classifier is based on the Bayes theorem. We understand that. A simple Bayesian classifier known as the naive Bayesian classifier. We discussed that. And it's supposed that it is supposing that the attribute value on a given class is independent of the values of other attributes. This is actually the downside to the naive Bayesian technique. These formula are available, the discussions are available, just in case that you wanted a written record of what different segments are. Hopefully, they're going to help you to move along with all of the items. What are we trying to do? At the end of the day, we want to look at the CI if X has happened versus CJ if X has happened, and then see which one is going to be the higher probability. Now, referring to the example we just discussed a moment ago in the previous session, we said CJ yes and CI no. So we had X event, a combination of outlook, humidity, and so on. And then we realized that the yes possibility happening, basically, is going to be 0.25 something, versus the no is going to be 0.9 something. So we realized that 0.9 is bigger than 0.2, and therefore we realized and we concluded that if X happens, it's going to go with the class of no at the end, at the target class. So that's what this page is trying to convey. We have mentioned that actually you can potentially calculate the probability by just looking at your sample. So this is what it is referring to. You don't have access to, for example, 8 billion people on planet Earth. You don't have access to 300 million people in USA. So what you do, you have a simple, a small sample. And with that sample, you could potentially calculate the probability. Is that exact? It's not, but it is close enough for our own calculation. So that's what we want to do. This one is a naive Bayesian classification. As you noticed, the P of CI is actually removed. It's a scale value. It's something that is constant. You saw at the end of the session we had in the previous recording that the P of X as being constant basically is going to act like a scale value. So here, remember that there is something we have not included. That would be P of CI. Okay, and then the list goes on. A little bit of a technicalities. You don't have to go through that, but I would like to go through an example. This is the continuation of an example we discussed in part 2, I believe, when we discussed decision tree. We had attributes, as we discussed, the RID, of course, does not help us anyway, because RID, the new row, is going to be 15, and who knows what 15 is going to be classified. So RID is actually not useful. These are just there simply for us to know the number of rows and how we could potentially utilize them to calculate the actual yeses and nos and youth and senior and so on. So that's going to be helpful. Age is an attribute, income is an attribute, a student and credit ratings are going to be attributes, and then the target is going to be buying computer or not. You want to classify as yes or no, binary in this case as well. With that in mind, I'm a cashier. I'm someone who is standing in a TV department, TV electronic department in one of the superstores, and I want to see whether you are interested to buy a TV from me or a computer from me. So this table, I have done a number of sales already. Although this table may not be available to me immediately as a Excel sheet, but I have accumulated the knowledge in my mind, and I have a good memory, and I'm going to look up the table in my mind. And then when you approach me, I'm going to see that you are a young person, and the way you talk, the way you explain, perhaps in an exchange of questions and answers we had together, I realized that your income is not bad. You have a good income. You don't seem to be a student, but your credit rating, if I do and check, is going to be excellent. Obviously, this says no. That would be surprised. I'm just making up this table, but obviously in real life, it would be a yes, maybe, right? Perhaps this no has happened because of different reasons. But this is a table, this is an example. We are trying to play a game, and it has happened to be no. So if I know that you are young, that your income is high, that you are not a student, that you have excellent credit rating, then I'm going to classify you already as no. What's the puzzle? What's the mystery? There is nothing. There is no mystery. You're already in my database. You're already in my data set. And therefore, the conclusion and the classification is already done. What happens if there is a combination that doesn't exist in my table? I want to classify that combination. We call it X, the event. So what is it? Consider classifier 1 correspond to the class buys, and C2 corresponds to computer to do no buys, okay? And the tuple, the X event, is age is youth, income is medium, student is yes, credit rating is fair. Youth, medium, yes, youth, medium, yes, and fair. That doesn't meet. If you examine this tuple, you can see that this tuple doesn't exist in my data set. Therefore, I have an obligation to classify it. So what, and of course, it is a question that has been asked of me to classify. You don't want to necessarily go exhaustively classify all of the remaining basically cases here. You don't have to. Keep in mind, this is extremely small. And in real life, we are talking about tens of thousands of rows and perhaps hundreds of columns. And that's going to be extremely time consuming to do that anyway. So we want to see which one weighs more. Will you buy or will you not buy? Which one is actually going to weigh more? If you have these attributes with the value noted, are you more likely to buy or are you more likely not to buy? I need to know that. So let's calculate the yeses and nos on the target table, target column. So this is nine yeses if you count them. It may be the same as what we have discussed in preceding table. Easy for me to copy and paste. And then you have 5 no's and then 5 divided by 14. So these are going to be on the last column. We did it on the last column. Very easy. Do that on the last column first. Then we are going to take a look at the buy yes and the age is young. The buy no and the age is young. And we are going to repeat that for all of the attributes, for example. So this is going to be 2/9, buy yes, and the age is 9. So, and then buy no, and the age is young. I'm going to count them. You are going to go here. Yes, no, yes, no. So that's 2 no's. And then youth no, that's 3 no's. Youth yes, that's 1 yes. Youth yes, that's 2 yes. And that's it. I'm missing one. Yeah, so this is 1 yes, this is 1 yes, that's 2 yeses. And 3 no's. Oh, yes, we are talking about nodes. So we are talking about nodes. So this is going to be 3 nodes out of 5, out of all of the being the youth. And then we have yeses and the age young. So what do we have? So we have yeses. We have 1 youth here, and we have 1 youth here, right? That's 2. And the number of yeses in total is 9, as we counted them before. Number of no's in total is going to be 5, as we counted them before. 5 plus 9 is going to be 14. So this is youth and yes, that's 2 over 9. This is youth and no, that's 3 over 5. That's what we are going to get. Similarly, medium and yes, that's 4 over 9. Medium and no, that's going to be 2 over 5. Again, this is another approach. I think the Excel file is a lot more organized. You could potentially take a look at that, but the approach is very similar, the same. Yes and a student yes, that's 6 over 9. No and a student yes, that's 1 over 5. 5 being no's and 9 being yeses. Yes and credit rating is fair, that's 6 over 9. No and credit rating is fair, that's 2 over 5. Again, 5 and 9 are the target column, the last column. Okay. Take a look at the tuple that we are looking for. We are looking at young, youth, medium, student, yes, and fair. But we are going to go and slowly calculate all of these components in the Bayesian theorem. So I want to say, if by is yes, what is the likelihood that X has happened? X being age young, income medium, a student yes, credit rating fair. If someone but yes, but the computer, what's the possibility that X was there? That combination existed. Okay, so for me to calculate that, I'm going to actually calculate all of the yeses together. Once again, go back to the Excel file, please. All of the yeses: age young, yes, income medium, yes, student yes, yes, and rating fair. You can also take a look at all of these calculations that we have done, the yeses together and the no's together. So I'm going to put them together. So that's what happens. And 0.044, and then the no's together is going to yield 0.019. Okay. Last step is the Bayesian theorem. So basically, we have by computer, of course, by computer, yes, is 0.643. I want to refresh your memory on this slide where we actually calculated the total yeses and the total no's. This is on the target column, 0.643, 0.357. So I need you to remember those numbers, grab a note and have them handy. What is happening? We got, let me go slowly up, 0.044 times 0.643, 0.019, and times 0.37, 0.57, and the results are going to be here. Now, the only difference is that I didn't calculate the PX. In this calculation, I did not normalize. We would like to normalize in the exam and the quiz. So please keep that in mind, because normalization allows us to maintain the relationship of the left and the right in the Bayesian theorem. So I would like you to go back to that Excel file and make sure you bring in the denominator. Although it's constant, although it's not changing, but that's the normalization that you need to do. Here we didn't do normalization, but still, since it's a scale value, we could potentially do a comparison right now. So 0.028 versus 0.007, I could say that yes is going to be the classification value. So the naive Bayesian classifier predicts Bayes computer to be yes for the tuple X, okay? Again, the scale is missing here, so please keep in mind P of CI is missing, but both of them are good. The approach is the same. It's kind of proportional, I would say. That scale value is going to be only basically helping us to understand the basically the proportionality. But if you put that scale value instead of proportionality, you're going to have equal sign. That would be the beauty of the Bayesian theorem, and I would recommend that you do that. So don't forget the normalization. Now, advantages, it is easy to implement, and it achieves good results. Disadvantages, we made an assumption. The assumptions are the conditions are actually independent. So of course, we are going to lose some accuracy. But we could potentially remedy that with a different network we didn't discuss in this class. We don't intend to discuss in this class. It's called Bayesian belief system, Bayesian belief network. And that could potentially help with the accuracy issue. Okay. Next, we are going to talk about neural network classifier. Thank you very much. Stay tuned for part 7, session 7, part 4.